As Tim mentioned, I'm Mike Tutkowski. I work at a data storage company out in Boulder, Colorado called SolidFire. And Tim, whether by design or not, actually had a few lead-in points from his previous presentations. So what I focus on in CloudStack is the storage component. The company I work for, we build an all SSD scale-out storage solution. So our main feature of the SAN is really this quality of service architecture, which I can get into in a little bit, and how it relates to CloudStack. But it's the ability to set a minimum and a maximum and burst number of IOPS. So as Tim mentioned, with other storage solutions, you may run into controller bottlenecks and not necessarily know how many IOPS you're getting to a particular volume. So that's one of the main purposes of our SAN, is to solve that problem and to give you predictable storage performance at cloud scale. So in general today, I'm talking about storage, but specifically I'm going to talk about primary storage. It as it relates to other things in CloudStack, like secondary storage, hosts, pods, zones. And, but the main focus is primary storage, since that's what I'm the most familiar with. So just a little bit here on CloudStack. As Tim mentioned, CloudStack is a cloud orchestration engine. So it handles the virtualization of your compute, your storage, and your networking, ideally to allow you to deploy and manage thousands of VMs with hundreds or thousands of hosts. This is kind of a top-down view of what CloudStack looks like, and I'll get to the primary storage component in a little while. But just to kind of give you a total view of what CloudStack actually is, it's broken up into these concepts of zones, pods, and clusters. So at the top level, you can see the zone, which oftentimes that equates to a data center, although a data center, if it's large enough, could have multiple zones in it. This is where you have your secondary storage, which is where a lot of your templates are placed, your backups. This is a lot of times very large quantities of storage used for deploying template images to primary storage later, where they can then be spun up into VMs. So at the zone level, you can have multiple secondary storages, one or more. As we dig a little deeper, we get into this concept of a pod. So a pod is basically a collection of hosts that are in the same rack, typically on the same subnet. So within a zone, you would normally have one or more pods. And then digging down to the next level, we get to the cluster finally, which is what with XenServer, I believe it's called a resource pool. So a cluster is where you tie together your hosts into the same compute pool. And at this level with CloudStack is where primary storage comes in. And although I'm only showing the single primary storage, you can have one or more primary storages per cluster, and the storage can be divided into shared and local storage. We'll get into details a little bit more on this as we go, but just kind of to show some of the common differences between primary and secondary storage. As I mentioned with primary storage, this is the kind of storage that's going to be used to run your virtual machines. And if your virtual machines are housing applications that require data disks, a lot of times like SQL Server might have a data disk, another disk for logs. These data disks are also housed on the primary storage. As opposed to the secondary storage, again, kind of repeat a little bit of what I said earlier, secondary storage is used to store ISOs, templates, backups, And then when you want to deploy a virtual machine to an actual host in a cluster, the secondary storage is where that template originates from, and it gets transferred to primary storage, and then it can be spawned off into a VM. So a lot of times with secondary storage, a lot of times you're dealing with lower IOPS, sequential reading, a lot of reading, not as much writing. And with primary storage, could be a lot of random I/O, tend to have a need for higher number of IOPS. And so those are just some of the basic differences between primary and secondary storage in CloudStack. So just to dig a little bit deeper into primary storage, since that's the area I'm going to focus on the most. As we said, primary storage is associated with a cluster within CloudStack today. That actually is changing with the 4.2 release of CloudStack, where primary storage can actually be placed at the zone level. But for production code today for CloudStack, primary storage is only at the cluster level. And as I mentioned, you can access multiple primary storages within a given cluster. And they basically service for root volumes and data disks. So the root volumes would basically be the drive that the VM is running off of, and then the data disk is applications that need additional storage. They can use these data disks. So as Tim mentioned, CloudStack supports several hypervisors, XenServer, VMware, KVM, Oracle Virtual Machine, does bare metal as well. I'm going to focus on, since obviously have a limited amount of time, I'm going to pick one of these hypervisors, and it's XenServer, so it's conveniently works out with Tim's presentation. And I'm just going to go into some of the details on how you actually set up primary storage for a XenServer environment. And just to kind of point this out, this is for CloudStack version 4.1 and earlier. This would still work in 4.2, but 4.2 has a lot of storage changes around primary storage being hostable at the zone level, so visible to all of the clusters. I'll get into that a little bit at the end of this presentation, but the bulk of the presentation is going to deal with CloudStack the way it works today with primary storage. So what we're looking at here is how you set up, how an admin sets up primary storage in CloudStack. And typically, well, my examples are going to come off of primarily off of SAN technology, since that's the most, that's my bulk of my experience. But you could see this using NFS as well. So what happens today is an admin goes off to the storage system, let's say the SAN, and they're going to provision a really large volume, so however many terabytes or whatever. They're going to provision that up front. And then they're going to go over to their hypervisor, so whether it's XenServer or VMware or whatever, with XenServer, they're going to create a storage repository, which I'll show the details of this in a little bit, but a storage repository is basically a XenServer data structure that is pointed at our SAN volume, and it can leverage that storage. And you can make these, since we're using shared storage in my example, the storage repository is actually a shared data structure. It's shared amongst the hosts in the cluster, in the resource pool, as XenServer calls it. So once you've actually got that hypervisor data structure set up, that storage repository for XenServer, it's called a data store for VMware. Once you've got that set up, this is when you transition over to CloudStack, and then you can create what's called primary storage, which is just what we say. They also call it a storage pool in CloudStack. But you can create this primary storage and base it on that hypervisor data structure. So in this case, I'll walk through slides that show us making use of a storage repository from XenServer. And then once you've actually created that primary storage, you can then, the administrator that is, can go in and make compute offerings, and what are called compute offerings and disk offerings. And they can tie it in to use that primary storage. So a compute offering is what collects information about how many processors we should expose to the VM, how much memory, where the VM's root disk should reside. So once you've created a compute offering, actual end users can go and execute instances of that compute offering, which will leverage the primary storage. And then data disk offerings is another option in CloudStack where you can specify, I would like this data disk to use SolidFire storage, let's say SolidFire storage, and you can then go ahead and arbitrarily have users create instances of that disk offering, which would give them a certain number of gigabytes or terabytes of space that can be used for applications that are running within your virtual machines. So if SQL Server needs a couple disks, one for the data, one for its transaction log, you can go and create execute the disk offering twice and make two different volumes that SQL Server can use. So let's go ahead and take a look at some of the details regarding how you actually go ahead and create this stuff from the storage side of things, and then going to the hypervisor, and then within CloudStack. So obviously storage, there's lots of options out there. Since I work for a data storage company, I'm going to use an example from my company's GUI to show how you might set up a volume. And in this case, it's very simple. You just put in the name of the volume, the capacity, and then below is a unique concept within our SAN, where not only do you specify the capacity of the volume, but you can dial in the minimum, maximum, and the burst number of IOPS for that volume. So the minimum is a guaranteed number of IOPS. The maximum is where you'll top off, except for in certain cases, like I think Tim might have mentioned boot storms, in certain cases where if you've accrued credits from not actually using all of your maximum IOPS, you can then burst above your maximum IOPS for certain extended periods of time before you're reeled back in to be at most within your maximum again. So we're just going to go ahead, set up this volume, name, capacity, IOPS. Once I've got the volume established on the SAN, in this case I'm using iSCSI, so I have an IQN, an iSCSI qualified name. And that is what leads us into XenServer and how I set up a storage repository within XenServer. So right here you can see I'm actually within what Tim talked about, Xen Center, and it may or may not be that easy to see on the slide there, but there's a button at the top called New Storage. So what I've done is I've clicked that button within this storage pool. I think it's just called Pool 1. So Pool 1, in my case, has 2 XenServer hosts. And I've gone to that pool level. I've clicked on the New Storage button. So this brings up a wizard, which we're going to just walk through. It's only a couple steps. There's a bunch of options in terms of how you can configure a storage repository. I'm going to focus on iSCSI, since that's what we export from our SAN. So there's a software iSCSI radio button. That's second one from the top. I've just selected that and clicked on the next button to move on to the following screen, which is where I provide a name for the storage repository. So the name here is what we're going to use from CloudStack to reference this storage repository. So just to kind of mention it here, it's SolidFire_gold, and we'll see that come up a little bit in the future slides. So I'm going to click on the next button, move on to the final page in the wizard, which allows us to stick in the IP address of the storage system. So I've filled that information in, and if you use CHAP, challenge handshake authentication protocol, which our SAN does use. You can provide the user and the password information below for the storage repository. And then it's really easy with XenServer here. You can actually query the storage system to see what IQNs are available, which is it's that button in the kind of the bottom right. Let's see, it says Discover IQNs, so Discover iSCSI qualified names. So this is going to come back and tell me all of the exported volumes from the storage system. I picked the one that I just created in the previous slide, and then the radio, actually it's a combo box right below it. It allows you to pick the LUN within the IQN. For our particular SAN, we just have a single LUN per IQN, so I just picked LUN 0. And then I can click on the Finish button to have created the storage repository. So at this next slide here, what we can see is not only do you have the resource pool, the cluster, you have 2 hosts within the cluster, and now you have a storage repository that's based on iSCSI called SolidFire Gold that's visible just below that second host. So now we're configured from the hypervisor point of view, and it's time to walk into CloudStack and actually set this up as primary storage, something that we can actually use. So I've logged in. I'm an administrator at this point, so this is not an activity that a normal user would perform. This is something that an admin would do. If you can't actually see it in this screenshot. It's a large enough GUI. I didn't want to shrink the picture down too small. But on the left-hand side, there's an array of buttons, and toward the bottom, there's one called Infrastructure. So I've clicked on that button, and then within the Infrastructure tab, there's a few options: zones, pods, clusters, hosts, primary storage. I've clicked on the primary storage button, and that's the window you're seeing here. So at this point, you can see I've actually just got a couple primary storages already set up within my CloudStack installation. And what this is actually with my 2 hosts within my XenServer's resource pool. When I added those to CloudStack, CloudStack automatically recognized the local storage on each of those hosts, and it added it as primary storage. So there was nothing you needed to do to actually add the local storage from each of those hosts. It was done automatically by CloudStack. So that's what you're seeing in this table here is my the local storage of my 2 hosts. What I'm going to do here now is I'm going to go to the upper right, and there's an Add Primary Storage button. Let's say I clicked on that. There's a subsequent dialog that shows up. So this is where we're actually able to point CloudStack at our storage repository that we just created. So you pick the zone that the primary storage is going to reside in. In my case, I just have a single zone. The pod is going to be the pod that your cluster is in. And in this case, I just have a single cluster. I just pick that one cluster. So now I'm telling CloudStack, this primary storage is for this cluster. The hosts in this cluster can access this primary storage. The name field, although I've actually stuck in an IP address, which may be a little misleading, it doesn't need to be an IP address for primary storage. It's just some name that you're going to assign to that primary storage. I think when I filled that in, I just had a single host in my cluster, and I just decided to use that IP address as the name. But there's no need to put an IP address there. You can just provide some name for the primary storage. The protocol in this case, there's a couple options for XenServer. There's different options for different hypervisors. But in this case, XenServer, I think it has an option where you can actually hook up iSCSI storage directly. You can tell CloudStack to go to the storage system and access that iSCSI qualified name and create a storage repository for you. The reason I didn't do it that way, I actually went into the hypervisor. is because CloudStack currently doesn't support CHAP credentials. So since I need CHAP credentials to access my volume, I had to go into XenServer, create the storage repository there, providing my CHAP credentials. If my volume, if I had an iSCSI accessible volume and it didn't require CHAP, I could have selected iSCSI from that protocol dropdown, and then you'd get different options below. But if you filled those in properly, then CloudStack would actually go out for you to XenServer and create a storage repository so you wouldn't have to do that step explicitly. So in my case, since I need CHAP credentials, I went ahead, I created my storage repository. Now I'm going to tell CloudStack that the protocol is what they call pre-setup. It's saying that I've already gone ahead and created a storage repository. On the hypervisor, I'll just fill you in as to which one I want you to use. And so the next row is the SR name label. That's the storage repository name label. So if you remember, we called that SolidFire _gold. And so that's the name you see in that particular field. So that's telling CloudStack, in this cluster, this XenServer cluster, I want you to use the SolidFire Gold shared storage repository. And then the row below that is the storage tags row. You can associate with this primary storage a bunch of labels that would be used later when CloudStack is trying to decide when you execute a compute offering, which would spin up a VM, or you execute a disk offering, which would create a data disk. The storage tags lets CloudStack know. So if the compute offering says, we wrote SolidFire Gold here as well for the storage tag, if your compute offering referenced SolidFire Gold as its storage tag, that would mean that that compute offering, if it's to be serviced, has to be serviced on a primary storage that has the label SolidFire Gold. So more than one primary storage can have that label. So when you execute a compute offering or a data disk offering, and it says its storage tag is SolidFire Gold, it's going to go and look through the primary storages in that cluster and see which ones have that label SolidFire Gold. And then any of those, as long as they have a sufficient amount of space, is free game to be used for the root disk for the VM or for a data disk, depending on what you're executing. And that might become a little bit more clear as we proceed through these slides. I haven't really gotten to a compute offering example yet. So once I've filled in all that information, I've hit the OK button. We come back to this, this table. Before we had 2 rows in the table. They were 2 local storages. Now we've got 3 rows. And it looks like the bottom row, the one that has the IP address for the name, that one is our shared storage that we just created. So you can see in the 3rd column, it actually references it as SolidFire Gold. That's the storage repository name. And it tells you which cluster it's in. So everything looks like it's set up just properly, the way we'd expect at this point. So now we can go ahead and create a compute offering. And just to kind of reiterate what a compute offering is, well, actually, let me get into that in the next slide. What we see here is we've actually got 3 compute offerings already set up in the table. I'm going to go ahead and click on the Add Compute Offering button in the upper right-hand corner. And then this dialog should actually make it a little bit more clear what a compute offering really is. So obviously a name, a description. And then what we're going to do here is we're going to provide information like how many virtual CPUs, what kind of memory, networking settings. And then as we get to the bottom, there's the storage tags field again. And we can see here I've actually written in SolidFire Gold as the only storage tag that can satisfy this compute offering. So when an end user comes in, this will be one of the compute offerings they can select. When they select this one, it'll spin up a VM that is serviced by primary storage that was labeled SolidFire Gold. In my case, there's only one primary storage with that label, so that's where it's going to end up. All right, so once I hit the OK button here, we can see there's 4 rows in the table. We've added our new compute offering to CloudStack. And I don't have any actual slides for data disk offerings, but it's really the same idea. We can see in the screenshot here, there's a select offering, kind of like in the middle, and it's at compute offerings right now. If you were to drop down that combo box, there's a disk offerings option. And if you go into that, it's really very similar. Instead of compute offerings, you have disk offerings. And you would go into the upper right and click Add Disk Offering. And it's actually less information to fill out. They just want a name, description, what kind of a size. So when a user executes this disk offering, how big should it be? And then that disk offering creates a volume that can be later attached to virtual machines. And then they can be leveraged within the operating system running within that virtual machine. So applications, kind of like I mentioned with SQL Server, they can have access to additional data disks. So compute offerings and disk offerings is kind of the takeaway there. Now this, I'd actually like to talk just a little bit about post 4.1 with CloudStack. So earlier I mentioned that primary storage is really at the cluster level today. So, and actually that's one shortcoming. Another shortcoming from a company such as SolidFire's perspective, where we actually guarantee IOPS to volumes. A shortcoming today with CloudStack is that you had to go ahead and allocate a huge volume up front. And on that volume, you run lots of VMs and have lots of data disks. Well, if you have lots of VMs, actually if you have more than one VM on one of our volumes, well, it'll work just fine, except for you will not be able to guarantee the number of IOPS on a per VM basis or a per data disk basis. So if I've got 10 VMs running on a SolidFire volume, the volume itself has a minimum, maximum burst number of IOPS. But the VMs and the data disks that are being housed on that volume, they're going to contend with each other for those IOPS. And so you won't be able to guarantee the performance of any individual virtual machine or data disk. So for a lot of use cases, that's okay. For some use cases, though, and what a lot of cloud service providers are beginning to realize is really a big market out there for being able to guarantee IOPS to virtual machines and data disks specifically, not to the big volume that a whole bunch of them are running off of, but to individual virtual machines, individual data disks. So the way this is being addressed in 4.2 is through a new storage framework, which allows companies, vendors such as SolidFire, to write logic that is specific to our storage system. So, for example, you don't, in this 4.2 version, have to go ahead and pre-allocate a huge volume up front. You actually introduce the storage system to CloudStack, not a particular volume within the storage system to CloudStack. So in 4.2, I'll have a plugin which will let CloudStack know, hey, this SolidFire storage system is out on the network. It's available to be used across clusters within a zone. And when people actually execute compute offerings or disk offerings, they will still be tied into that storage through the storage tags field. But dynamically, what happens behind the scenes is when a user comes in, they want to execute a compute offering, that will be serviced from their point of view the same way it always has been. But behind the scenes, what's going to happen is, okay, well, that, let's say data disk offering, 2 gigabytes. that volume didn't exist until the user actually executed the data disk offering. Then at that point, we've gone off to the SolidFire SAN, we've created a 2 gigabyte disk, and we've set the IOPS based on fields that will become available in 4.2 for the data disks, so that you can actually specify how many IOPS, min, max, bursts. So we'll go off, create that volume, and then we'll set up the XenServer storage repository or the VMware data store behind the scenes, so administrator doesn't have to worry about that either. And when that process is complete, CloudStack will have a new volume to access for that cluster. So what this allows us to do is actually have a single virtual machine or a single data disk run on a single volume with guaranteed IOPS. So that way you can basically, cloud service providers have a really cool new feature. They can offer guaranteed IOPS. Doesn't necessarily have to be always a huge number of IOPS. Maybe it's a desktop application and you just want to make sure you have within a certain range. Well, that's fine. It can be a high number. It can be a low number. The basic point is that you can individually provision IOPS separate from capacity, whereas in the past, those two concepts were often coupled. If you needed more IOPS, a lot of times what you did was you had to buy more disks, and so you really were pretty low utilized on the capacity side to get the right number of IOPS. And even in that case, unless you had a dedicated resource, you didn't necessarily know how many IOPS you were going to get to a particular VM or a data disk. So that's the main use case behind the SolidFire SAN, is to provide cloud service providers and large enterprises this ability to be able to guarantee IOPS on a per VM and per data disk basis. And that's one of the main things I'm working on at the moment within 4.2. So at this point, I think I've basically concluded what I wanted to talk about. Were there any questions anyone had? Yeah.
Yeah, so when you provision the repository, storage repository, do you tend for having multiple machines on it? Or do you see instances where people actually have a repository per machine? No, I guess the reason I'm asking is you cannot control IOPS per machine regardless.
Mm-hmm.
Right? So you're just reducing that zone of failure, essentially, with noise paper.
Yeah, let me make sure I understand. I'll try to repeat the question. So it sounds like you're curious when you create a storage repository within XenServer. So the way I did it was with XenCenter, what you do is you add the hosts in the cluster to XenCenter, and then it recognizes that they're part of they're part of a compute pool. And then you go to the compute pool and you actually begin the process of adding the storage repository. And so at that point, as far as I know, each of the hosts within that cluster is aware of that shared storage resource. Now, within a storage repository, you can have one or more virtual disk images. So those could be root volumes or data disks and whatever is needed for your VMs. So a given VM is probably going to typically have access to a particular VDI exclusively.
So I don't think that's my point. So the point I was trying to make is that if you have a number of tenants on the same, sharing a repository, whether it be, you may have tenants that share 2, 3, 4 different repositories,
yeah.
But you'll have tenants potentially. So I guess what I'm trying to get at is that
I think I know, yeah.
If you're isolating IOPS, you're isolating IOPS to a LAN that you're exposing, whether it be iSCSI, fiber channel, FCOE, I mean, you name it, IRDP, whatever.
Yes.
The issue remains that you're controlling the IOPS on the LAN. However, you may have a single noisy neighbor that takes down however many other machines within that repository, right? So you're reducing the zone of failure, effectively saying, instead of potentially taking down an entire SAN, we're going to take down this particular LAN, right? Let's
see. So maybe let's make sure I'm understanding. So The way you do it is actually on a volume by volume basis. You pick that minimum, maximum, and burst number of IOPS.
The volume being a repository.
And I like the noisy neighbor reference because that actually is the main goal, is to eliminate the noisy neighbor. So normally if you got a noisy neighbor, he ruins performance or makes it unpredictable for all of the other guys on that same volume.
Right.
So in this case, your neighbor would be on a separate volume with a separate dedicated number of IOPS, and it can max those out without affecting any of the other volumes on the SAN.
Right. So this is assuming you know who the noisy neighbors are. Right.
Actually, you don't even have to worry about it. So if you have a single VM running on a single volume, and you've tied in a minimum, maximum, and burst number of IOPS per volume, the guy that used to be the noisy neighbor, now he's running on his own volume. So he is free to max out that volume for IOPS without touching any of the other guys. Now, if you look at him in the performance monitor and you see he's always at maximum number of IOPS, and you want to grant him more IOPS, you can do that dynamically as well through the GUI or the API and give him, as long as the SAN has those resources available, you could say, okay, I'm going to bump this guy's resources up. He's going to have a higher number of IOPS, and you don't have to bring anything offline to do that.
Again, this is assuming you know who the noisy neighbor is, right? This is kind of like saying if I'm running in rack space and I've got 10,000 tenants on this one cluster, I know exactly who the three bad guys are, or who the three noisy guys are.
Yeah,
right?
I don't see why you shouldn't have to know about the noisy neighbor at all. So,
because you're saying you isolate to individual volumes.
It's isolated on a volume by volume basis. Exactly.
But a volume is shared by a number of machines.
Well, what happens is the machines share it in the sense that they each have a little bit of metadata up front to know. So actually, I think that's the point we want to get at, is that in CloudStack today, I think what you're saying is true. A single volume would house multiple virtual machines.
Right, exactly.
Yeah, but in 4.2, a single volume will only house a single virtual machine. Okay. And even though that volume is visible to each of the hosts within the resource pool, only one is really using it at a time. So if you need to dynamically move the VM to another host, that's fine, that can happen, and then that new host is the only guy who's running that VM. So today, if you want to guarantee IOPS to a virtual machine or a data disk, and when I say today, I mean 4.1 or earlier, it is possible, and I've actually documented a way to do this with API calls to the SolidFire SAN, to the hypervisor of choice, and then to CloudStack. What it entails is actually creating data disks and compute offerings that are only executed one time. And so it is completely doable, but it's not nearly as convenient as it is in 4.2 where you have this plugin framework. And then with the plugin framework, it's so much easier. Just tell CloudStack, I've got this storage system, and then each volume gets only a single VM or a single data disk, and then you can guarantee IOPS. And then you don't have to worry about noisy neighbors at all, which today, if you're doing it the easy way in 4.1, yeah, it's just a big iSCSI volume with a certain number of IOPS that's guaranteed to that particular volume, but the VMs and the data disks, they compete for resources. And that's what we want to get away with 4.2. And like I say, it is possible in 4.1 and earlier. It's just there is some legwork for the cloud service provider or the large enterprise to go ahead and implement some custom code.
So 4.2 and beyond is still going to be a iSCSI backend?
Well, I should say 4.2 and beyond, it's going to be this storage plugin framework. And whether it's iSCSI is not necessarily, I mean, it is iSCSI, but it's possible it could be implemented by other vendors to support other protocols.
So agnostic to some degree.
Yeah, it should be relatively, I mean, right now it's just going to, 4.2, I think it's just going to be iSCSI, but that's only because I believe SolidFire is the only vendor that's implementing a plugin to do this kind of, I mean, I don't know of any other vendors that do this kind of detailed IOPS control. I mean, there are other vendors that talk about quality of service, but they're talking about it more in terms of relative performance control. So almost like threads within an operating system. Well, my thread has higher priority than your thread, so I'll get more attention from the CPU than you will, but you can't guarantee how much more attention. We call it more like hard quality of service, where you actually will get a minimum number of IOPS up to a maximum number. There is no relative performance based on whatever else is running in the system. Just like you have a certain amount of capacity, you have a certain number of IOPS. And you are guaranteed that minimum unless you go ahead and over-provision the system, which is you're free to do. But if you don't do that, you're guaranteed, even in fault conditions. So that's one of the interesting points, too, is that it's not like this controller up front that can get overwhelmed, and if you have failure conditions, you really lose performance. This is a distributed, clustered system where each of the nodes load balances data and IOPS. And so the real push here is, even during failure conditions, to be able to guarantee minimum IOPS. So as far as I know, we're the only plug-in for 4.2, but it could be extended in the future.
Cool.
Yeah, you okay? Okay. Yeah, did you have a question?
Yeah, the SD-RAM caching type of solutions, where is it typically implemented? On a NAS level, or you know what I'm talking about? If you have
Yeah, so what happens, maybe I'll just answer it from a general standpoint and see if it answers your question. So in our case, it is an all SSD-based solution, which I know a lot of people, they think, oh my goodness, that's going to be expensive. So there's a lot of data efficiency technologies within the SAN to bring that cost per gigabyte down in line with a traditional hard disk-based array. So every volume is thinly provisioned. Every volume benefits from deduplication of 4 kilobyte blocks across the whole SAN. All the data coming in is compressed. So in a lot of cases, especially if you have similar disk images, data coming in, if it's already written to SSDs, we know about it in the cache, and there's some updating that goes on, but not actual rewriting of data to the SSDs. So the SSDs are just the wear in general is extended based on the way the system is designed. And let me think. I think you also mentioned something about a cache. So the data that comes into the system is written to like an NV RAM card, and it's cached up, and then eventually it's written to 2 locations on the SAN, depending on the way the database is. There's a database that maintains configuration information. Each volume is distributed across all of the nodes in a cluster, and so even though your data is initially being written to one of the nodes, it's being cached right away, and then eventually it's distributed to 2 nodes where it's written to SSD if it's not already there, if there's not a copy across the system that happens to have that particular byte configuration. So I'm not sure if I really answered what you were asking there, or do you want to?
I think so. I was trying to get the trend. Where is this going? So, a complete SSD SANs is where everything's going, or is there still some hybrids of SSD for caching or quick access?
Yes. So all of the persistent storage is SSD in this system. And then there's just this, I believe it's an 8 gigabyte NV RAM card per box. So basically all of our hardware is standard Dell 1U boxes. And the only real customization is this NV RAM card. So it's pretty much off-the-shelf hardware with SSDs that we've written the logic to write to the SSDs in such a way as to extend their life, and also just keeping in mind the intricacies of our system. So we don't, the main concern for us, because quality of service is our biggest, I don't even want to call it a feature really, because it's really the system from the ground up was architected with quality of service in mind. That is the main purpose of the SAN. A lot of people talk about quality of service as a feature. From our point of view, it's an architecture. It's got to be built from the ground up to support this kind of concept. And so for us, with these SSDs, one of the things is we need consistent latency. So We don't want like garbage collection going on at indeterminate amounts. We can't rely on the SSD drive to do certain things for us. We have to do that ourselves so we can control all of the aspects of when data is garbage collected and how all that works. And then also, we need to make sure when you add storage nodes into the cluster, which the cluster you can maybe start with 4 or 5 storage nodes, and then as you need to, you can, it's kind of a pay-as-you-grow type model. So as you need to, you can buy additional storage nodes and then just add them into the cluster. And behind the scenes, the data will just be migrated to the appropriate, it'll just be migrated to be distributed evenly across the cluster, which is another way of being able to guarantee load balancing, making sure the IOPS, the minimum requirements can be met.
Thank you.
Yeah, no problem. Anybody else? All right, thanks a lot.